direction, and then this meant the Hamiltonian matrix representation is, we would take for our base states, we would calculate H squeezed between two base states. So this would be H sub I prime, the matrix element H I prime. So H itself would be the matrix H11, H12, H21, H22, where this is, in our case, the state Z plus, H, Z plus, and then Z plus, H, Z minus, and then Z minus, H, Z plus, and Z minus, H, Z minus. And but we know that H on Z plus was now H bar omega 0 over 2 Z plus, and H Z minus was H minus H bar omega 0 over 2 Z minus. So the matrix representation for H then is H bar omega 0 over 2 0 0 H bar omega 0 over 2. Okay, so that's, and we can call, if we call H bar omega 0 over 2 E0, then we can just, then H is E0 0 E0. Okay, so that's, things to note. Question? Okay, so things to note are, one, that H is diagonal, and two, off-diagonal elements are 0, and they are things like Z plus, H, Z minus, and Z minus, H, Z plus. Okay. Now, in our vector space, Z plus and Z minus are two orthogonal directions. It's not exactly the same as two-dimensional real space, but we can draw it in the following way. We can draw it inaccurately, right? We can put some axes here that define Z plus and Z minus as orthogonal axes, although this isn't entirely correct. But in any case, if that's the case, we already discussed how you can rotate vectors, right? So Hamiltonians can rotate state vectors. Okay, and it doesn't have to be a rotation in the sense that we talked about an actual rotation about an axis. I'm just saying that you can move, if we had, you know, a set of, even though we defined some kind of coordinate system, z plus and z minus, which we might have some state vector psi that looks like this. And if we operate it on, with some Hamiltonian, it might actually change it to, you know, something that looks like this. So h hat psi can be rotated. It doesn't have to point in the same direction. Okay? In particular, this means that if we have, you know, the Hamiltonian generates time translations. So we can, you know, this might look instead like psi of t points in this direction, and then at some later time, psi of t plus, you know, delta t points in a different direction. So the state vector is rotated, or is changing in time. So this is the Schrödinger picture. Okay, so in your Hilbert space, in your state space here, you've got, you know, the psi itself can be doing some, you know, some kind of crazy rotations or movements or whatever as the Hamiltonian generates the time evolution of the system.
So I mean, this psi t plus delta t is the same as the h.
Right.
Delta.
Yeah.
Okay. So if, and then you, over there, the h equals that matrix with E0, and E0 is h bar. Omega 0, that's the, oh, okay, so that changes things. Okay, that makes more sense.
Oh, wait, okay, yeah, whatever.
The omega 0 is the angle, right?
No, that would be that's the frequency of rotation.
Frequency of rotation,
Of
okay.
precession in a magnetic
Okay, I
field.
understand. And so would that just be adding t to it, or?
Well, I'm not being specific. I'm just saying that if I operate with h on my state vector, I can get a rotation.
Okay, I see.
Okay, it doesn't. Yeah.
Okay.
I'm being more general now.
Okay.
Oh, okay. So. Now, this doesn't, for this particular Hamiltonian, so let's call this thing star. So for this Hamiltonian here, no matter what state vector you write down, you won't get a change in time because these matrix elements are zero. What that says, this says that that H does not rotate Z plus or Z minus into one another. It does not connect the states. Okay? So this, when you have a Hamiltonian that's diagonal in your basis states, right? There's a representation of our Hamiltonian in some basis. When it's diagonal in that basis, then you have stationary states. They don't change. Okay?
Well, it's like the identity matrix.
Hmm?
It's like well, no, it's because it's negative, but that's negative is there, so you, anyway, go ahead.
Well, it's diagonal, right?
Diagonal,
Yeah.
not
There's no off diagonal elements, so none of the states are connected. So that means the Hamiltonian is represented in the basis states here are the stationary states of the system. Okay, and so the consequence of this is we always want to find the stationary states. Of the system. Where the Hamiltonian is diagonal. And this is not always possible. But it's a goal to find the stationary states of the system. Okay. So let's consider two-state systems in particular. So we're already talking about a two-state system because this state of the spin can be either spin up or spin down, and so this is a two-state system. So now there are just many two-state systems in nature, so not just spin one-half systems. So let's consider, for example, let's consider the ammonia molecule. So the ammonia molecule has a nitrogen atom, and then it has three hydrogen atoms that form a plane. Any 3 points form a plane. And the nitrogen atom sits above or below this plane. so the nitrogen atom can tunnel from one side of the H3 plane to the other. So we can describe two configurations. We can consider this configuration or this configuration. And we can label them. So let's just call this configuration 1 and that configuration 2.
So I don't wanna digress too much, but like, so it doesn't just rotate, like the whole molecule, it like essentially like reverses itself, like as if like the location of the 3 hydrogens stays the same, it's just their location relative to the nitrogen changed.
Yeah, I mean, it can rotate. Well, so it's, it's a lot more complicated than this, right?
Mhm.
So, I mean, in reality, the molecule itself is undergoing all sorts of vibrations.
Mm-hmm.
So if you look at the molecule itself has 4 atoms, and they're each connected by some kind of, bond. And so you have normal modes for the system. So you have, you'll have a nitrogen mode where it's just doing this against the hydrogens, and then you'll have a breathing mode for the entire molecule where it just goes like this.
Yeah.
And then you'll have a mode where the nitrogen stays still, and you'll probably have the triangle going, getting bigger and smaller. So, during one of those times, that potential will get kind of small, and the nitrogen can pop through.
Okay, I see.
But I mean, probably there's some tunneling probability there as well. So. Okay, so you can consider the nitrogen molecule in one of these 2 states if we want to just simplify it. So this is the simplest picture of the nitrogen states. And so if, just by symmetry, these states have equal energy. E0. Okay. So if there's no tunneling from one state to the other, then we'll have the Hamiltonian for the system will give us 0 matrix elements that are 0, so H will not connect the 2 the states 1 and 2, and H for the system then would just be E0, 0, 0, E0. Okay, and if there were, let's go over here. Can I erase all this stuff? Did you guys? If the nitrogen atom can tunnel, from one side to the other, then H will connect the states. we'll have something like H two is equal to minus A and two if it's symmetric. Again, this would be minus A, where A is some amplitude. It's a tunnel. So in this case, H will be E0 minus A minus A E0. Okay? So for, let's call this H over here H0 because it's has no tunneling. So for H0, which is just the diagonal, which with no tunneling, what are the stationary states?
It would be, I guess it'd be, so it'd be bra 1 H0 hat, and then 2, no, it'd be 1 cat, right? So it'd be 1 H0 1, like in the bra cat notation, right?
Well, just the state, not the amplitude.
Oh, okay.
What are the stationary states? What are the stationary cats?
1 and 2.
Good. Okay, so those are the stationary states for that case. Now we have for H that's equal to E0 minus A minus A E0. We need to find the stationary states. Okay? Because now the nitrogen atom can flop back and forth. So to do this, we diagonalize the Hamiltonian. Okay, which means find the eigenvalues and eigenvectors. Okay, so the eigenvalues will be these will be the new eigenenergies. And the eigenvectors will be the new stationary state vectors. Okay, so this is just an exercise in linear algebra. So to find the eigenvalues, we just take the determinant of E0 minus lambda minus A, E0 minus lambda, and this must be 0, so we have E0 minus lambda squared minus A squared equals 0, so we can bring the A to the other side. We'll have E0 minus lambda is equal to plus or minus A, so lambda, I want lambda. equal to, E0 plus or minus A. Okay, so we have lambda plus minus. Okay, so, let's find the eigenvector for lambda plus. That means we have to take our matrix. We have to multiply it times some vector, uv, and we'll try to find uv, and then this has to be times lambda plus. So that would be E0 plus A uv. Okay, so this is E0u minus A times V is equal to E0u plus A times U. So I can cancel an E0u, the A's cancel, and so I have U is equal to minus V. So the eigenvector is U minus U. Okay, and we can normalize. So if we normalize it, then we'll have if these things are equal, I mean, it's pretty obvious this is going to be 1 over the square root of 2, 1 minus 1. Okay? So we have this eigenvector is paired with E0 plus A. And then for lambda minus, we'll have E0 minus A, E0, EV is equal to E0 minus A. So we're just working out the top line here. We have E0u minus AV is equal to E0u minus AU. So again, we can throw away our E0u's, and now we have the U equals V. So we have 1 over the square root of 2, 1, 1 is the eigenvector that goes along with E0 minus A. Okay, any questions about that? Okay, so when we wrote this Hamiltonian out here, this implies that we're implicitly stating that the vector, the ket 1 is this, and the ket 2 is the column vector 0, 1, okay? That's just, and so when we have these eigenvectors here, let's call them, I'm going to be consistent with my notes here. We'll call them capital 1 and capital 2.
So you can always have a prime to it.
Did you say capital 1 and capital 2?
Roman 1 and Roman 2.
Oh, okay.
I see.
Let's do Roman 1 is the addition of them. So let's do this one for Roman 1. So okay, and so these are the states that we get, just these are these two states. And so the Hamiltonian this is the Hamiltonian in basis, in the basis 1 and 2, right? That's the basis that's Hamiltonian is written. So now, what we just found was that there are eigenvectors and eigenvalues, and eigenvectors and eigenvalues mean that there is, we can write the Hamiltonian in the basis capital 1 and capital 2, or Roman 1 and Roman 2, and it will be diagonal. Okay, and so to touch base with what we did before, we should have H on capital 1, which is the one plus the plus in it, should be E0 minus A 1, and H on 2 will be E0 plus A on Roman 2. Okay, so H will be equal to E0 minus A, 0, 0, E0 plus A in this basis. Okay? Now, this is the mechanics as easy as you can do it. So we didn't really do any time dependence of anything in here yet, so I want to do that next. But this is how it works in the most simple way. If you write down a Hamiltonian, you know the basis that you write the Hamiltonian down in, obviously, or you couldn't write it down. But when you write the Hamiltonian down, then you want to find the eigenvectors and eigenvalues so you can find the stationary states. Okay, so these are the new stationary states. Are there any questions before I do the time dependence?
I have more of a curiosity question. So earlier you said that it's not always possible to find the stationary states.
Yeah.
I'm assuming the part where that would make it impossible is that, because I think I remember that there are some matrices that you can't find determinants of. What would go wrong in this?
If H is time dependent.
Oh, really? Okay.
If it's changing.
I gotta spoil it a little bit then, because it's not stationary. I guess that makes sense.
Yeah, you can't do it. But in general, in most of the problems that you encounter, and you can find the stationary states of the system. Does everybody believe me that you can do this, or do you want me to work it out explicitly? There's a couple of ways to do it. So, how would you all work it out?
First, I would Google how to do matrix algebra again, because I forget every time.
Wait, okay. What was the question exactly?
If you want to show that these states are give you a diagonal Hamiltonian, how would you do it? And what's really the only thing you can kind of do?
Well, I guess if you go back to our thing over here where we have, if you would match it up i's with the 2's and the 2's with the i's, and then see if it's 0, and that's.
Wait, say that again?
If you do, like here, 1, 2, 1 H02 is supposed to be 0.
Yeah.
And so if you do the 2 E minus A1 over Roman, the Roman 2 with the, if you evaluate the rocket as, instead of pairing Roman 1 and Roman 1, you would do Roman 2 and Roman 1 to see if it's 0, and that would be a way to.
That would tell you the off-diagonal elements, yeah.
But if they're 0, then you, if you do that at 0, then it is, if the ones that don't match are 0, then you know it's diagonal. And if they, does
Sure.
that make sense?
Well, okay,
That's
yeah,
not-
sure. But I mean, yes.
Is that not doing math enough?
No, that's right. I mean, you can do that, yeah. I mean, the first thing that you should maybe check is that, you know, you can check that this is true just by using the definitions here.
Oh, okay.
If I take the dot products here, I'll get 1, this will give us -1.
So you can
this
just like
is-
dot through.
That's 1 minus 1 equals 0. What's that?
I'm saying, how can you just like dot through and kind of
You know,
rebuild it?
That's what Adam was
Yeah.
saying.
Okay. Yeah, for some reason I thought you were asking if you could do it without using that definition or something, because I thought like, oh, we can't use that.
No, you can. Of course you can use this. Yeah.
Okay, so yeah. Then that makes sense.
Okay.
If it's diagonal, then they have no component in relation to each other,
Mhm.
and so that's why it's 0.
Yeah.
They're more orthogonal, I guess.
Well, this is orthogonality,
Right.
and then this just says that the states aren't connected by the Hamiltonian. So it won't rotate one of them into the other. So these are actually important states in chemistry. So so let's consider a proton with two protons with 1 electron. And so you can either have the state where the electron is around the first proton, or the state is around the second proton. Okay. And it's again it's the same exact thing that we wrote down. It's the same math and everything. So, the two stationary states are 1 and 2. Where the electron is exchanged between the two protons. Okay, so if you look at an energy diagram, it looks like this. You have proton 1, this is the unperturbed energy E0, and then when you turn on the hopping, so I'm drawing now a diagram that you see in an energy diagram that you see in chemistry. So this is the sigma bond, and this is the sigma star bond. So the state with low energy, stationary state with low energy, sigma is the bonding. That's the bonding orbital, and sigma star is the anti-bonding orbital. Okay, so this is really one of the major bases of chemistry. So this is for two protons. The electrons are in s orbitals, and that's why they use sigma here. So this is proton-proton, bonding, or hydrogen bonding, if you want to look at it from that perspective. And in more complicated materials, you have higher orbitals in like the D transition metals, and if you look at the periodic table, the D transition metals have really much more complicated electronic structure. The electrons are in much higher energy orbits, and they have lobes and things like that, and so you get directional bonding in solids because of the lobes of those. The electron orbitals have have specific angles between the lobes, and those things bond specifically, can bond specifically, and so that's why you can have things like diamond and whatever. But you can look at all of the chemistry of bonding in solids from this perspective, because it's just electrons that are being shared between two nuclei. All right, and it lowers the energy. So the exchange of an electron between two protons lowers the energy and makes them attract. This also extends to particle physics, because you can look at the attraction of, for example, an electron and a proton, or you can look at the repulsion of two electrons by the exchange of particles. So particle exchange is what gives us forces. So electrons repulse each other by exchanging photons and that kind of thing. So that's the basic quantum mechanics of a two-state system and some particle exchange. So let's look at the time dependence now. So are there any questions before I continue?
Just one. So, how did you know that the amplitude is 1 over square root of 2?
It was 1 over what?
How do you know that the amplitude there is 1 over square root of 2?
Because if I want to normalize this vector,
Oh, just because you want to know what? That's right.
Yeah.
Okay. Yeah, that makes sense.
that'll be 1 plus 1 over 2.
Yeah, that makes sense.
Okay, so let's look at the time dependence now, because this gives us a little bit more information about what's happening. So again, we will assume first that H We have H0, which is just E0, 0, 0, E0 for our two states. And let's write the Schrödinger equation. Out by hand. So we'll have, remember the Schrödinger equation is IH bar, partial with respect to time, of psi of t is equal to the Hamiltonian acting on psi of t. Okay? Now, if we have a two-state system, psi of t will be some constant C1 of t times state 1 plus C2 of t times state 2. I can write the Schrödinger equation that way. And so if I take the time derivative here, what do I have? I have IH bar, take the time derivative here, I'll have C1 prime of t times 1 plus C2 prime of t times 2, and that has to equal h hat on psi. And so this will be C1 1 plus C2 2. Okay? Now let's just take this equation and let's dot through from the left with 1. So if I come in from the left with 1, well, I'll get this term here. This 1's going to hit this 2 and give me a 0, so I'll have IH bar C1 prime of t is equal to, and on the right, I'll have C1 and then H11, because I'm going to be squeezing H between the two states 1, 1. And this matrix, after all, is just H11, H12, H21, H22. So that's C1, H11 plus C2, H12. So I'll have that equation. Okay. And then if we dot through this top equation by 2, I'll have IH bar C2 prime of t is equal to C1 H21 plus C2 H22. So we'll have these two differential equations. Okay, so these are two coupled differential equations because I have the time derivative of C1 depends on C1 and C2, and then I have another differential equation, C2 prime, that depends on C1 and C2. Okay, so, but for H11, or sorry, H12 equals H21 equals 0, this is really simple. Then I'll have IH bar C1 prime of t is equal to, well, H11, that's just E0, and H12 is going to be 0 in this particular case. So this will just be, this will be E0 C1 t. And so we just have, what's the solution to this equation? C1 prime of t is equal to minus I E0 over H bar C1 of t.
Doesn't E0 also contain H bar?
Doesn't what?
Doesn't E0 also have H bar? So would they cancel or no?
No.
Okay. I think it was in the specific case they had E0 equal to, I think it was like omega 0 over H bar or something.
Yeah, but this could be anything.
Yeah, got it.
So how do we solve that equation? What's the solution to that equation?
What are we solving for?
C1 of t.
So
So then,
natural log of 1 over, because you bring the C1 over and then you integrate and like, oh my goodness.
what
You're
function can you,
integrating.
what function can you take the derivative
Oh,
of and you get
e.
the function back?
E to the.
Right.
Right, it's exponential, right? So this C1 of t is C1 at 0, some constant, times e to the minus I E0 over h bar t,
Mm.
okay? And then likewise, C2 of t must be some C2 at time 0, e to the minus I E0 over h bar t. Okay, so this is trivial. What does this mean? So this means that the state ket, it doesn't matter what you start off with. C1 and C0 can be any two constants. Normalization requires that the magnitude of C1 0 squared plus the magnitude of C2 0 squared equals 1. That's just a normalization requirement that we've come across before. So if we had any state psi that was equal, that has is C1 1 plus C2 2, I can write that as e to the minus I E0 over h bar t times C1 0 1 plus C2 0 2. Okay? And that's a stationary state because you can pull all the time dependence out and you have a ket that doesn't have any time dependence.
I see.
Okay, that's what stationary means. Because this is just a phase factor now, but the ket always points in the same direction. In the Hilbert space, this thing's always pointing in the same direction. The phase changes with time, but that's no big deal because any measurement that you have.
The phase is observable, right?
Hmm?
Isn't that gonna be, when you take a measurement, it just kind of goes away?
Right, any kind of expectation value you have for any operator, you'll have a e to the plus over here and you'll have an e to the minus with the ket, and then so they'll just cancel.
Right, because phases are unobservable in quantum mechanics, right?
Okay, so that's the stationary state. Now, somehow we should get back to all this stuff when we do the non-stationary state. When we put in the amplitudes. Okay, so for the interacting Hamiltonian, we have H is equal to E0 minus A E0. And so we'll have I H bar C1 prime of T is equal to, just go back to this equation, we'll have E0 C1, and then we'll have minus A C2, and then the other differential equation will be C2 prime of T is equal to minus A C1 plus E0 C2. So we'll have these two equations we have to solve. Okay, so now it's not as obvious how to solve these.
Oh, he actually wants to solve them?
Hmm?
He actually wants to solve them?
So we gotta find the eigenvalues or the eigenenergies, I think is what you called them last time. Right?
Well, now we're solving differential equations now.
I see. Well,
But are we gonna first diagonalize H?
No, well, we're kind of doing it by solving these differential equations.
well, I mean, don't we know what C1 prime equals?
Yeah, it equals E0 C1 plus minus.
Well, I meant it also equals,
No, this is for a different problem.
Yeah, that's
okay,
different.
we're
Right,
gonna-
that's for the Hamiltonian with no.
okay, got it. Um,
Okay, so it's, you need to, you just wanna simplify them so that you can solve it. So one way to do it is to just,
Right, oh,
You have to
yeah, you have to
integrate.
take a,
Can you
you have to
integrate?
find the characteristic equation of the differential equation.
well, let's just keep it simple.
You can solve for C two instead of equal to each other? maybe?
Oh, yeah, you could do elimination, couldn't you?
No,
Well, I mean,
You can-
well, C two is a constant
Oh,
in
but
the,
C two isn't, because C two.
no, it's not.
no, it's not a constant in that differential equation?
No, the functions of time, I just didn't write it down.
Oh.
Yeah.
Oh. I
So
see.
the easy way to solve these are to just add and subtract the equations.
Hmm.
So if we add the equations, then we'll get
Oh, that's what I meant by elimination, I meant like,
C1
subtracting
plus
one
C.
equation from the other.
2 prime is equal to, okay, so if we add them, let's see, I'll have E0 minus A, C1 minus A, let's see here, plus E0 C2. So IH bar C1 plus E2 prime is equal to E0 minus A. There's our E0 minus A. C1 plus C2. Okay, so this is just structurally, it's the same as this equation here. So that means we know that C1 of T plus C2 of T, this combo here is equal to some C1 0 plus C2 0 times E to the minus I, E0 minus A over H bar times C1 plus C2.
Oh, is there supposed to be a prime there on the left side?
Oh, wait, no, I integrated.
Oh, you after integration, got it.
So we've got that equation, and then if we subtract subtracting them, we'll have IH bar C1 minus C2 prime is equal to, now obviously we'll get E0 plus A, C1 minus C2. So C1 minus C2, I should call this T, whatever. This is equal to C1 minus C2 at time 0, E to the minus I, E0 plus A over H bar C1 minus C2. Okay? So we've just found we've identified the stationary states then of the system. Because we found a linear combination. Of the state coefficients. That has simple dependence. Okay, so if we know that C1 plus C2 has simple time dependence and C1 minus C2 has simple time dependence, then we've effectively solved it. So, okay, so let's, so now we can add in, let's call this equation, let's call this equation 3 and equation 4. Now we can add and subtract three and 4 to recover C1 and C2. Okay, so we have, what do we have? We have C1 plus C2 is equal to this constant C1 0 plus C2 0, e to the minus, e to the minus, what is it? E0 minus a, I'm just gonna not write the other stuff. C1 plus C2 plus C1 minus C2 is equal to C1 0 minus C2 0, e to the minus E0 plus a, C1 minus C2. So if we add them, we'll have 2C1 is equal to, this is painful. Call that alpha and this beta. So we'll have alpha e to, I want to just simplify this and call this minus, and I'll call this e plus. So this is alpha minus C1 plus C2 plus beta e to the plus C1 minus C2. Okay, so this is alpha. If I group C1 and C2 now, let's see here. The minus. I've got alpha e to the minus plus beta e to the plus C1 plus alpha e to the minus beta e to the plus C2. Okay, look, when we solved this equation here, you guys are supposed to catch me. All right, when we solved this equation and we integrated, there's nothing here. I was confusing the hell out of myself. Okay, I was like, what did I do? Because that can't be right. Okay, so all right, so what do we have here? Yeah, that's a lot simpler. Okay, so C1 is equal to alpha over 2 e to the minus I over h bar E0 minus AT plus beta over 2 e to the minus I over h bar E0 plus A times T. Okay, and then subtracting. We'll get something similar for, if we, let's see, if I subtract the bottom one from the top, then I'll have alpha over two this minus this stuff. So I'll have alpha over two u to the I over h bar. 0 minus at minus beta over two e to the minus I over h bar. 0 plus a t. Okay? Now you can already see for a certain choice of the initial conditions, you know, what happens. So if C1 of 0 is equal to 1 and C2 of 0 is equal to 0, that means alpha is equal to 1. See, if C1 0 is equal to 1 and C2 of 0 is equal to C2 0 is equal to 0. Alpha is 1 and beta is 1. So C1 of t then will be, okay, we'll have 1/2. Let's see here, I want to pull out, I have, what's a term I can pull out here? My E0s have the same, everything's, the sign is the same in both exponents, so I can pull some stuff out. So let's write this as e to the minus I over h bar E0t, okay, times 1/2, and then I'll have e to the minus I over h bar at plus e to the plus I over h bar at. Right? So this is just the cosine of at over h bar. So C1 of t, the magnitude anyway, squared, this term will just go away. It'll just be cosine squared at over h bar. And then you can calculate C2 of t squared. You'll get this is a minus sign, so you'll get a sign. Okay, so if I start off in state 1, then it just does this. So if this is state 1, it starts off in state 1, and then state 2 just oscillates with time. Okay, so at time 0, cosine's 1, at time 0, sine is 0. So the thing just flip-flops back and forth. Excuse me, but if you're in one of the stationary states, so if, you know, if C0, 1 was 1 over the square root of 2, and they were both 1 over the square root of 2, then the difference here, beta would be 0, and alpha would be 1. And so you would just have a time dependence that went like E0 minus a. So you'd be in the stationary state. It wouldn't change.
It'd be a straight line.
It'd be a straight line. It should be a constant. Okay. So this,
the y-axis on that plot,
yeah, that's
the probability there.
Yeah, it's the probability that a measurement would find it in state.
Okay.
Would find it in state 1 or state 2. Okay. So that's the difference between a stationary state and a non-stationary state. And it's also the difference between, it's also, you know, that, it's a very, you know, quantum characteristic. You know, because you can't, when you talk about the ammonia molecule, for example, you know, you have that picture where the nitrogen atom is just on one side. If it tunnels to the other side, it just pops over there. So it's, you know, it's really just popping from one side to the other. It's not like slowly moving through. Because that probability, the probability to find it on any particular side grows and falls. But in actuality, it's just there and it can pop over, it can tunnel over.
And like it being in between isn't really an allowable
Right.
position for it to be. It has to bond at a certain angle.
Yeah, I mean, it could be an actual forbidden region, right? The potential would look like this, and so if the particle has, it has no, you know, it's forbidden to be inside here. Okay. All right, everybody have a good week.